Okay, test. The YouTube stream should be good now. The volume should be on at least. Let's hope so. Let me know if not. Okay, so where were we? When we left off, we just finished up with electricity, right? And so now what we're going to be doing is we're going to be getting into magnetism. And now, so there's a lot of similarities and differences between electricity and magnetism. And the first similarity is that magnetism is also described using fields, right? So all of the concepts that we kind of developed with electric fields. So, for instance, the force that's exerted on a charged particle will also sort of still apply here. We will still be determining forces on charged particles, for instance, except that the formulas are going to be a little bit different. And what we're going to see is that the force actually depends on the speed at which the charges are moving, and that's the one main difference between these two fields here. Okay. So a bit of a review of grade 11 physics if you want to look at the iPad screen now. So yeah, similar to electric fields, we use magnetic field lines to indicate the strength and the direction of a magnetic field. So magnetic field lines extend from the north pole of the magnet and enter into the south pole. And so I actually have a little video here. Let's see how this is going to work. Okay. So we have a little box, and a guy puts a bar magnet inside the box here. And inside the box is a whole bunch of iron fillings. And so when he inserts it, you can actually see the iron fillings start to move towards the two poles of the bar magnet. And you can start to see the way that the field lines orient themselves around the bar magnet, which I thought was pretty cool, right? So essentially, magnetic field lines permeate all the space around it. We just can't see it, right? So fields in general, they permeate the space around whatever is generating the field, but you can't visualize them. However, they do exert forces. So in this case, we can see that they're exerting some sort of force on the iron fillings that are suspended in this glass tube here. All right. But all the same concepts that we kind of developed with electric fields sort of will still apply here. Okay. Okay. So back to the iPad screen. One thing, it's important to recognize that electric fields and magnetic fields, or electricity and magnetism, are kind of two sides of the same coin. So when we have some sort of charge that's moving, although it does generate its own electric field, it also generates a magnetic field. And this is kind of the main takeaway from a lot of scientific research in the late 1800s, is kind of bridging electricity and magnetism together to make electromagnetism, right? So it's not electricity and magnetism, it's electromagnetism, and they both definitely influence each other, okay? And so one thing that you should have seen in grade 11 is the Oersted Principle. And the Oersted Principle, which we'll talk more about in a second here, is that when you have a current-carrying wire, the moving charges within that wire generate or produce a magnetic field, okay? So as we see from this picture here, when we have a current traveling through a wire, the magnetic field gets generated around it, okay? So this is a... Oh, we're doing magnetism, Tycho. So this is section 8.1. This is actually the stuff that we're starting with here is just a review of oh wait, hold on one second. Hey Tycho, are you in the group chat, or are you back to it here. Okay, so yeah, has everyone seen this concept, Oersted's Principle, in grade 11? Did everyone see that? The magnetic field generated by a current carrying wire, and you developed a whole bunch of... Yeah, the thumb points in the direction of the current, and then the fingers wrap in the direction of the magnetic field. Yep. It's the right-hand rule. We're actually going to be covering a lot of different right-hand rules today. So do some stretches, do some exercises, get the right hand ready, because we're going to be using it. All right. Okay. Yeah, and we have a few different... Pardon me? They do, but it's moving charges. Moving charges produce a magnetic field. So a stationary charge will not produce a magnetic field. It's only the movement of charges that produce a magnetic field. We'll see that in a second here. Yeah. Cool. Okay, yeah, just like you said, Aiden, to determine the direction of the magnetic field around a current carrying wire, what we do is we put our thumb in the direction of the current, and then we wrap our fingers of our right hand in the direction of the magnetic field. So the one interesting thing about the magnetic field that differs from the electric field is that the field actually is circumferential around a current carrying wire, which is a little bit different. Okay, and I know most of you have taken calculus at this point. And in calculus, we learned that anytime we're using the right-hand rule, what we're really doing is taking a cross product. Okay, so and that goes for this as well. So we are taking a cross product here. It's just kind of hidden away, right? We'll see some mathematics in a second, and what we're going to notice is that there's going to be a formula that looks really, really similar to the magnitude of a cross product. Okay, but just know that whenever we're using the right-hand rule of any kind, we are in the background doing a cross product that gives us the direction. Okay. Does everyone remember what a solenoid is? So this again, a coiled wire, exactly. Yeah. So a solenoid is a conducting wire that's just wound into a coil. Okay. Now, because the coil is wound like this, when we apply our right-hand rule, it turns out that in order to apply the right-hand rule correctly, what we do is we wrap our fingers in the direction of the current around the coil, and then our thumb points in the direction of the magnetic field in the center of the coil, in the center of the solenoid. Okay. I found a typo. Thumb, not thumb. That's so embarrassing. Whoops. Yeah, so this is specifically the right-hand rule for a coiled wire, right? So a solenoid, okay? And that should all be review of grade 11. So 8.1 is kind of just let's get back into magnetism because it's been a while, right? So my recommendation, if you're still kind of unsure about magnetism, maybe read through 8.1 or check through your old notes from grade 11. I know when I did the grade 11 physics class, we did magnetism right at the end, so we didn't really get a good chance to really dig into it. So depending on how you guys found it when you guys went through it, make sure you're kind of comfortable with, like, in general, what magnetic fields are, okay? Because a lot of what we're going to be doing from here on out is kind of just plug in a lot of formulas, but it's difficult to understand what these formulas are doing without a good intuition of what a magnetic field is. Okay, so yeah, just kind of keep that in mind. All right. Okay, so onto like the new stuff, I guess. Okay, so again, magnetic fields, as I've been mentioning, they're kind of similar to electric fields, right? So they're similar in that they exert a force on charged particles, but the key difference here is that magnetic fields exert a force on moving charged particles. Okay, so if you have, say, an electron and you just put it into a magnetic field and you keep it there, you don't touch it, it won't move anywhere. There's no force exerted on it. Okay, and so this is a pretty big distinction from what we were seeing with electricity, right? When we had an electric field, we had our formula. So we had our F equals K Q1 Q2 over R squared formula. And it didn't matter if these charges were moving. In fact, we often considered these charges to be stationary, and we did all of our calculations based on that, right? So stationary charges can feel a force in an electric field, but they can't feel a force in a magnetic field, and that's the big difference. Okay. So magnetic fields, they are measured using Teslas. So 1 Tesla is equal to 1 kilogram per coulomb per second. Okay, and so 1 Tesla is actually a very extreme magnetic field. I think I have an example problem later on here that uses the magnetic field strength of Earth, which is something like, actually, let's see if I have it here. Magnetic field strength of Earth. I think it was something like 57 micro Tesla. So you can see that magnetic fields are generally, like 1 Tesla is a very strong magnetic field. So the Earth's magnetic field is, 57 micro Tesla, very, very small. Okay. Okay. So let's get into some actual calculations here. So the force that a magnetic field exerts on a moving charge, we can find it using this formula. Okay. And so force, the magnetic force instead of the electric force, is equal to QVB sine theta. So Q is the charge, V is the speed that the charge is moving at, B stands for the magnetic field, or the strength of the magnetic field, and then theta is the angle between the direction that the charge is moving in and our magnetic field. Okay. Now again, this should look very familiar, right? We know that from calculus, if we have again, don't worry if you haven't seen calculus yet, because we're not actually going to be doing any cross products or anything like that. But in calculus, we saw that we have A cross B equals the magnitude of A, magnitude of B, sine theta. And so if you kind of compare these two formulas, you should definitely see some similarities there, right? We get the magnitude of the velocity. We get the magnitude of the magnetic field. We get sine theta, where theta is the angle between them. So definitely there is a cross product going on here, which we're just kind of not paying attention to. So if you want to see it, Fm equals Q V cross B. Exactly. Yeah, the charge just kind of hangs out. It's sort of along for the ride. It's not part of the cross product though. We're just multiplying the cross product by a scalar quantity, the scalar quantity being the charge. Yeah. Okay. Any other questions? Are we doing okay so far? Good so far? Okay. So, now, because this is a cross product, we actually have to figure out a way to consider direction, okay? And so this is where the right-hand rule comes in. So to determine the direction that the force is exerted on the moving charge, what we have to do is we have to point our thumb in the direction that the charge is moving, right? So we point our thumb in the direction of the velocity. Our pointer finger points in the direction of the magnetic field. And then the middle finger or palm points in the direction of the force that's exerted on the charge, okay, on the moving charge. So we have the velocity, so V, which way the particle is moving. We have B, that's the magnetic field, right? And then our middle finger points up in the direction of the force, okay? Does everyone see that? Again, I hope it's not mirrored, but this is my right hand. And so, yeah, the right-hand rule tells us what direction the force would be exerted on. Okay, so as we're going to see in a second here, when we get to this example, oftentimes we're going to be using the formula to calculate what the magnitude of the magnetic force is, and then we're going to be using the right-hand rule to figure out what direction the force is going in. Okay. Okay, let's get into an example. All right. So we have an electron This electron is moving at a speed of 54 meters per second through a magnetic field, and the magnetic field has a strength of 1.2 Tesla. And we're also told the angle between the electron's velocity vector and the magnetic field is 90 degrees. So that'll definitely simplify our calculations, okay? Because sine of 90 is 1, right? So that'll make it a lot easier. Okay, so let's write down our givens here. So the speed at which it's moving is 54 meters per second. The strength of the magnetic field is 1.2 Tesla. And the angle between the velocity vector and the magnetic field is 90 degrees. Okay. So now let's figure out the force that's exerted on that charge. Okay. So Fm equals QVB sine theta. Okay. Now let's plug in all the things we know. So Q is negative 1.60 times 10 to the negative 19 coulombs. V is 54 meters per second. B is 1.2 Tesla. And then sine of 90 degrees. And I said this simplifies our calculation because sine 90 is just 1. So that's easy. We don't have to consider it anymore. Now, I put in this charge as a negative. Now, the negative, actually, when we're talking about force, we're not going to get a negative force, right? That negative is going to tell us something about the direction of the force, okay? And so we'll get to that in a second here. And so really, I don't really have to focus too much on this negative sign. We'll get to that when we answer part B here. Okay. All right, I'm going to plug these in. I get a value of 1.038210347 newtons. So approximately 1.0, 1.0, yeah, times 10 to the negative 17 newtons. Okay. Are we all good with that? So any questions so far? Are we good? No. So in this example, 90 degrees, yeah. But really, the angle is the angle is between the direction that the charge is moving and the magnetic field, right? So those don't have to be 90 degrees whatsoever, right? As we'll see in the next question, what we're going to have is a proton that's moving through a magnetic field, but it's kind of at an angle, right? And so the angle between them won't be 90 degrees anymore. All right. So we'll see. It would see that's exactly, yeah. So what we're going to see in the next example, we're going to see this. We're going to calculate the initial magnitude of the force and the initial acceleration, because yeah, you're right. As soon as it starts feeling that force, it's going to change direction, and then everything's kind of off the table, right? What we're actually going to see in I think tomorrow, we're going to see how charges are actually going to move within a magnetic field, and it actually ends up being a circular motion problem. Okay, so all the stuff from what was it, chapter 3, will come back, right? We're going to have to deal with centripetal force and centripetal acceleration again. So we'll see that. Okay, let's finish up this question though. So yeah, we figured out the magnitude of the magnetic force on the electron, which is good. Now let's consider what way or what direction the particle will feel a force, right? So we have our velocity is going in one direction. We have the magnetic field. Now those are perpendicular to each other, right? The velocity and the magnetic field are perpendicular to each other. Okay, so we should let's say the velocity is to the right, the magnetic field is forward ahead of us. Then the force exerted should be up, right? According to the right-hand rule. Okay, so velocity to the right, force directly in front of us, or velocity to the right, magnetic field directly in front of us, force up, right? Does that make sense? Kind of. So if the force is up, yeah, Costa, I'm seeing yours is kind of upside down here. Yeah, like that, yeah. So velocity to the right, force directly in front, or sorry, velocity to the right, magnetic field directly in front, force up. Everyone kind of see that here? We're good with that? So velocity to the right, magnetic field in front, force up. Okay. Now there's actually a bunch of different ways that there are, yeah. So if you apply a rotation, you'll actually get the same direction. So there are many variations of the right hand rule. What I do is I do my first quantity, my second quantity, and then my third quantity, what I'm calculating, right? So A cross B equals C is the way that I always do my cross products, my right hand rules. Okay. So if we're oriented this way, right? Velocity to the right, magnetic field directly in front of us, force up, that would be the case. However, again, we have this negative sign kind of in the way, right? And so that negative sign, what it's going to do is it's actually going to flip it, right? So instead of the force being up, because the particle is negative, the force will actually be down. Okay? So that's the one place that you have to be really careful with this. The right-hand rule applies for positive charges. When we have a negative charge, which we do in this case, we have an electron, what it does is it actually flips the result, right? So if we figure out that our force is up, because the charge is negative, the force will then be down, okay? So we have to be kind of careful about that. And I think I write that in the notes here, right? So note that this works, the right-hand rule works when the charge is positive. Yeah, go ahead. Yeah, exactly. Like you use the right-hand rule the same way, except that when you get your final answer, so if I say, oh, the force is up, because the charge is negative, the force is down. It just flips the direction entirely. Yeah. Does that make sense? Yeah. Okay, cool. Any other questions on that? We're doing pretty good. Okay, I have one more. Oh, sorry, go ahead. So the direction is not negative. The direction is just opposite what you do get when you use the right-hand rule, right? So if we use the right-hand rule and we figure out that the force is upwards, then because the charge is negative, the force is not actually upwards, the force is downwards. Okay. So the right-hand rule essentially... Yeah, exactly. The negative sign in this equation tells you that we're actually flipping it because the charge is negative. Yes. Cool. Okay. Okay. Let's do another example. Aiden, you kind of jumped the gun here, which is good. Let's figure out what happens when the angle is not 90 degrees. Now, nothing actually changes. The only thing that does change is theta is not 90, so sine theta is not 1, okay? Okay, so next example. So a proton is moving along the x-axis, and it's moving with a speed of 78 meters per second. It enters a magnetic field with a strength of 2.7 Tesla, and the angle between the velocity vector and the magnetic field is 38 degrees this time, okay? So not 90. And now, Costa, what you were saying, we can only really consider the initial magnitude and direction of the magnetic force, right? The reason being is that when the proton enters the magnetic field, it will feel a force, right? And so because it feels a force, it will also accelerate in a certain direction, which means it's the direction of the velocity vector will change, okay? Now, if the direction of the velocity vector changes, then suddenly the direction of the force will also change, right? And so that's where we have to kind of be a little bit careful with this. We can only really say what the initial force and what the initial acceleration will be. because as soon as we let it go into the magnetic field, then it will start changing direction and the force itself will change. Okay? Okay, so let's get to this. Yeah, you probably could. Yeah, I mean, that becomes challenging because if the force is changing, then the acceleration is changing, right? And if the acceleration is changing, then our kinematics formulas that we built up in chapter 1 don't work anymore, right? And if our kinematics formulas don't work, then we're in a bit of a tricky situation, right? So yeah, doing some sort of numerical calculation would probably allow us to figure out how this thing will move through time. Now, what we're going to see tomorrow, we're actually going to see a simplified scenario of this where we do let the particle go into the magnetic field and we're going to see how it's moving. However, it's sort of a pretty specific scenario that we have to build up to get there. Okay, but we'll definitely see what these particles will do once they enter the magnetic field. We'll see that tomorrow. All right. Okay, so let's go with this one. So the proton here is moving along the x-axis. Okay, so our velocity is 78 meters per second, and the velocity vector is pointing in the positive x direction. Okay. It enters a magnetic field of strength 2.7 Tesla. Now, I didn't write down what direction the magnetic... Oh, it's just the angle. We know what the angle is between the two, right? So we have our velocity vector, and then we have our magnetic field that points... I mean, again, as we saw with that little video at the start, the magnetic field permeates all of this space here, right? So the magnetic field, I think we're assuming it's a constant magnetic field, so it's not changing as the particle moves. So the magnetic field everywhere is 2.7 Teslas, and the angle between them here is 38 degrees. Okay, so let's first calculate what the magnitude of the magnetic force is going to be. Okay, so the magnetic force is given by QVB sine theta. So the charge is, this time it's positive, right, because it's a proton. So positive 1.60 times 10 to the negative 19 coulombs. Times the velocity vector, or the speed, so 78 meters per second, times the magnetic field strength, so 2.7 Teslas, times sine of the angle between the field and the velocity, 38 degrees. So let's work out what that's going to be. So constant 23 times 78 times 2.7 times sine 38. So I get a value of 2.07735 times 10 to the negative 17 newtons. Okay. So that ends up being approximately 2.07. How many sig figs? 2 sig figs? 2.1 times 10 to the negative 17 newtons. Okay. So that gives us the initial force that the proton will feel, right? So again, any moment later, it will feel a different force, right? Because it'll change directions and then everything kind of goes off the table, okay? But let's figure out what direction the force will be, okay? So we have our velocity is pointing to the right, okay? Our magnetic field is kind of pointing at an angle relative to the velocity, okay? Which means our magnetic force, now this is a really hard thing to visualize here. So the velocity is pointing to the right, the magnetic field is pointing at an angle relative to that. The magnetic force that's being exerted on the proton will actually point out of the page, okay? Does everyone see that? So again, velocity points to the right, the magnetic field points at an angle up, and so the magnetic force is going to be back towards us, right? Based on this picture here. So the magnetic field is actually going to point out of the page. Or sorry, the magnetic force is going to point out of the page like that. And the symbol that we use for that is this little dot, right? So this little dot means out of the page. Okay, and the whenever you see a cross like this, that means into the page. Except for 0, right? If the particle is pointing in the same direction, yeah, 0 is kind of like the odd one out. But any angle, and it'll still point out of the page. All right. Okay, so let's keep going. Yeah. Okay, so let's figure out the. Yeah, that's okay. That's okay. I figure there'll be disruptions here and there, but I think it'll be good. Okay, so we have the initial magnitude of the magnetic force. Now let's figure out the initial acceleration of the proton. Okay, so for this, we know what the force is. We can look up what the mass of the proton is, so we can figure out what the initial acceleration of the proton will be. Okay, so this is just F equals ma. All right, so there's part A. For part B, F equals ma. Oops. And we can rearrange for the acceleration. Acceleration equals force, the magnetic force from part A over the mass of the proton. Okay, so we have 2.077, 17 newtons, mass of the proton. (1.67 times 10 to the negative 27 kilograms. Okay, so let's plug that in. Yeah, you got to think it would be a high acceleration because the mass of the proton is so tiny, right? So we get 1.241 blah 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 times 10 to the 10 meter per second squared, or approximately 1.2. Okay. Okay. Any questions about that example? Are we feeling pretty good? Excellent. Excellent. Okay. So that's it for magnetic force exerted on single charged particles. Okay, so all of the stuff that we did, this Fm equals QVB sine theta, that's for when we have a single point charge that's moving at a certain speed within a magnetic field. Okay, so that's where this formula applies. Okay, so a single point charge traveling at a certain speed, moving in a magnetic field where we know all of these quantities. That's where this formula applies. Okay. However, now this goes back to what you were saying at the start, Costa. We very rarely just deal with single charges, right? Often we deal with many charges moving together, right? We deal with some sort of current or how the charge is changing with time, right? And so usually, I mean, it often makes more sense to consider, okay, what's happening when we have current flowing through a wire? How is the magnetic field generated from that? Or what is the force exerted on a wire that is just placed within a magnetic field? Okay, that's probably a more applicable question to ask than what is the force that's just being exerted on a single charge that's moving in a magnetic field. Okay, so the magnetic force that's exerted on a current carrying duct. Yeah, I hear an echo. Thank you. Yeah, okay, cool. Okay, so let's figure out the force that's exerted on a current carrying wire. Okay, so what we're going to do, let's assume that we have a wire. Okay, and what we're going to do is we're going to consider a little segment of the wire, and the segment of the wire has a length of L. Okay, and let's say that within that small segment of the wire, there's Q amount of charge within that small segment. Okay. And so we know that the force, now let's say we take this wire and we throw it into a magnetic field, okay? So we know that the force that's exerted on this small piece of wire will be Fm equals QVB sine theta, right? Okay. Now, we might be wondering, okay, well, this formula is good. We know that we have the charge. Let's say we know we have like an ambient magnetic field, let's say, hanging around here. But how do we know how fast these charges are moving, right? So this actually goes back to a concept that hopefully you covered in grade 11. Essentially, it's a way of relating current to the flow of charge, or how the charge is changing with time, okay? So let's say that within, let's imagine that we have like a little charge hanging around here, right? So we have a little charge hanging around here. So if this charge is moving, if this charge is flowing through the wire, let's say it moves a distance L in a time delta t. Okay? So what we can do is we can actually use that to determine the speed of the charge. So the speed of the charge is equal to L over delta t, the distance over the time, right? And what we're going to do is we're going to plug that into our magnetic force formula. So Q L over delta T times B sine theta. Okay. Now I'm going to do some rearranging here. So I'm going to have Q and over delta T. This is actually the formula. Q over delta T from grade 11 is the formula for the current. So I is the current. And I is measured in amperes, or amps, A. Exactly, yeah. So we're kind of imagining, we're like zooming ourselves into the wire, and we're imagining a single electron is flowing through this wire, okay? Obviously, we can't actually do that, but what we're trying to do here in a really kind of hand-wavy way is relate what's going on microscopically to the macroscopic system, right? Because current is a macroscopic quantity, right? We can measure the current through an entire wire. We don't have to know what a single charge is doing, okay? What we're doing here is we're kind of using the microscopic point of view to build up to the macroscopic point of view. Okay, so what I can do is I can rearrange this formula a little bit. So I'll have Q over delta T times L B sine theta. Oh, now Q over delta T is the current. And so I have I L B sine theta. And that is the force that's going to be exerted on this entire length of wire, okay? So a little derivation, nothing too crazy. All right. So yeah, F, the force that's exerted on the wire is dependent on the current, the length of the wire segment, the strength of the magnetic field, and the orientation of the wire segment with respect to the magnetic field. Okay. So again, the right-hand rule actually still applies here. Okay. So the thumb will point in the direction that the charges are moving in, right? So in this case, the charges are moving in the direction that the current is flowing, right? So, and again, Costa, this goes back to your point. We're using conventional current here, okay? So this is where things kind of get a little strange, but yeah, the thumb points in the direction of the current, the finger points in the direction of the magnetic field, and then the middle finger points in the direction of the force that's exerted on the wire, okay? Okay, so let's do an example here. So we have a piece of wire that is 45.2 centimeters long and through that wire we are running a 12 amp current. Okay, the wire is placed in a magnetic field. Wait, the wire moves through a magnetic field. Yeah, I mean, we have a wire and we're just placing it in a magnetic field. It will move, right, because it will experience a force. Okay, and we have to figure out what the strength of the magnetic field, or we have to figure out what the magnetic force on the wire is, depending on the orientation of the wire. Okay, so we're going to consider 3 different orientations here. We're going to have the, let's say this is the wire, so this is the direction that the current is flowing in, and then here we have, let's say we have the magnetic field in red. Okay, so we have it, this is case A, when theta is 0 degrees. Okay, so the wire is perfectly aligned with the magnetic field. We have B, so the case where the magnetic field will keep the same, but then the wire that we place inside of it will be oriented at an angle of 45 degrees. Okay. And then we have the case, the last case, where the magnetic field and the current, the wire, are oriented 90 degrees apart from each other. Okay. Okay. So let's consider each of these 3 cases, and then we'll summarize what we're noticing about the magnetic field, or the force exerted on the wire here is. Okay. So let's get to it. So we know that the force on, actually let's write down the givens that we have. So we're told that L is equal to 45.2 centimeters, which is 0.452 meters. We know the current is 12 amps. Okay, and so, and we also know the magnetic field strength is 0.30 Tesla. Okay. Okay, so let's figure out the force that's exerted on the wire. Okay, so we have ILB sine theta. So because we have sine of 0, this is actually just 0, right? So this whole thing is just 0. So that means when the wire is oriented in the same direction as the magnetic field is pointing in, it doesn't experience any force at all. Okay, so when the wire, or when the current is parallel to the magnetic field, there is no force exerted on the wire. Okay, now let's figure out what the force will be when the wire is oriented at 45 degrees. Like what the force is? No. Well, I mean, let's make sure here. So the thumb points in the direction of the current. Your okay, hold on. So yeah, your thumb points in the current. Your pointer finger points in the direction of the magnetic field, and your palm or your middle finger points in the direction of the force. So we're not necessarily worried about, because keep in mind here, we're using conventional current, right? So what we're imagining here, even though this is not the case, is that the charges that are flowing through this wire are positive charges. So the right-hand rule that we developed, the VBF, is still applicable here, even though we know that there are technically electrons that are flowing through the wire, not positive particles, right? So this is the case where conventional current can kind of mess you up, but yeah, just know that we're not imagining electrons flowing through this wire. We're imagining positively charged particles flowing through the wire. Okay. Yeah, like the magnitude will be the same. However, if we consider electrons flowing through it, it should be opposite, right? However, the right-hand rule, again, still applies, right? So current, magnetic field, force. As long as you remember that, I guess I should say conventional current, magnetic field, force. That's the key here, okay? So we're not considering what's actually happening in the wire. We're not considering the fact that electrons are the particle that's flowing. Okay. All right, let's finish this guy off here. So sine 45. 12 times 0.452 times 0.3. So I get a value of 1.15 newtons. Okay. And let's do the last one here, just to see how it'll change. So F wire. In this case, sine 90 is 1. So sine, the sine function is at a maximum. So we should expect this force to be higher, and indeed it is. So the force that's exerted on this wire is approximately 1.63 newtons. Okay. So we can see that as the wire is pointed more perpendicularly, as the wire is pointed more perpendicular to the magnetic field, it the force that's exerted on that wire increases. Okay. Any questions about that example? Okay, alrighty. So let us. I only have one more example. All right, so we'll finish this up, and then that is it for today. But we'll still explain. Yeah, one more example, and that's the entire lesson. So, but we're still going to explain kind of how I think. Yeah, what I think we can kind of do. I have a cool idea, and we'll talk about that at the end. But let's get to this here. So. 2 electrical poles support a current carrying wire. So we have, let's draw out a picture of this, right? So we have a one pole, one power line, and we have a wire between them. Then we have another power line, okay? And if we look at a segment of the wire, so we assume that the segment of the wire has a length of 2.5 meters. Okay, and the mass on that segment is 0.44 kilograms. Okay, within that wire we have a 15 amp current flowing through it. So the current flowing through it is 15 amps. The conventional current is oriented to the east. Okay, so this current is flowing, this direction here is east. Okay. And that'll be important because it'll tell us what orientation the force will be. Okay. The magnetic field is oriented north. So let's say we're looking at this picture from like the side on. Okay, so you're standing on the sidewalk or whatever, and you look up and you see 2 power poles. And what we're doing is we're looking at the wire connecting the 2 poles. And so if the wire is pointed towards the east, or the current is flowing towards the east, the magnetic field obviously points towards the north, right? Because we're on Earth, that's the direction that the magnetic field lines point, right? And so in this picture, because I'm looking at the side on, we're going to imagine the magnetic field is pointing into the page. Okay, so into the page. All right. So the magnetic field is 57 microtesla, and it's north. Okay. But north in my diagram is into page because I'm looking at it from the side. Okay. Okay, and 57 microtesla, that is 57 times 10 to the negative 6 Tesla. Okay, so I'll convert that before we start plugging it in. All right. Okay, so I think I have everything here. So I have the mass, I have the length of the wire, I have the mass of the wire, I've written down the current. Okay, and now what we have to do is figure out the magnitude and direction of the magnetic force. Okay. So for that, we're going to be using our the force on the wire is equal to the current times the length of the wire segment times the strength of the magnetic field times the sine of the angle between the two. Okay. Now, because the current is flowing towards the east and the magnetic field is pointed north, the direction or the angle between those two directions is 90 degrees, right? They're perpendicular to each other. And so sine of theta is sine of 90, which is 1. So we don't really have to worry too much about the sine of the angle there. Okay, so the current is 15 amps. The length of the wire segment is 2.5 meters. The magnetic field is 57 microtesla, so 57 times 10 to the negative 6 Tesla. And then I'm not worried about sine theta, so let's plug that in, see what we get. I get a value of 2.1375 times 10 to the negative 3 newtons. Okay. And now let's consider what direction that force is pointing in, right? So we have the current flowing towards the east. We have the magnetic field points towards the north. Does anyone want to guess at which direction the magnetic force will be? Not so, because we have east, north. Here, it's probably easier if I do this. Let's do this, right? So I have east, north, right? So the magnetic field will actually point up, if that makes sense. Yeah, right? So yeah, east is the current, north is the magnetic field, up is the force that's exerted on this wire. Okay. So by the right-hand rule, the force is directed up. Okay. Okay, so which means that we have a magnetic force that's actually pulling the wire up, which is actually really interesting. So you might wonder, it's like, oh, could you, in theory, you could run a current through here that would support the wire entirely, right? Like if you had a high enough current flowing through this wire, it would perfectly counteract the gravitational force that's exerted on the wire, okay? But let's see what the gravitational force is, right? Just to imagine what current we would have to send through this wire in order to get it to perfectly balance, in order for it to be in equilibrium. My guess is it's going to be a pretty big current. Yes, I think you could. I think you could. But keep in mind that this is like this wire is connected to two poles, right? So it's not going to go anywhere, right? And so it would be very difficult to run a high enough current through something in order to get it to fully levitate, right? Even this, like 15 amps, I think is a pretty levitating current. Yes. All right, Costa, you get on that. Let us know your developments tomorrow. It's just the way that I have my diagram oriented, right? So it's kind of like it's kind of the limitations of me drawing on this board here. Okay, here let me get some. Give me a second here. Let me get some pencil crayons. This will make more sense hopefully. Actually, I wonder how maglev trains work. That's one thing that on your guys' assignment that's due Friday, I posted like a couple applications of magnetic fields. If you guys want to research how maglev trains work, I'm sure you could dig into some pretty cool stuff if you wanted to do that as part of your assignment question. But okay, so Aiden, to go to your question here. So yeah, this is kind of difficult to do in one dimension here. Even on the camera, it's going to be difficult. So let's say this orange marker points towards the east, okay? Now this pink marker, let's say it points towards the north, right? So right now we have east is the orange marker, pink is the north marker, okay? Now, what I've done on my paper is I've oriented it so that north is basically directed into the page, right? The reason why I did that is when we use the right-hand rule, what we find is that the magnetic force, so the blue marker is the magnetic force, is directed upwards, okay? The way that I have this oriented here, right? So imagine you're sitting in your room right now. So imagine you point yourself in the north direction, right? So to your right is going to be east. Yeah, it's easier when you start to like fiddle with pencils or markers or whatever, or even just like put yourself in the situation, right? So exactly, yeah. Oh, yeah. That makes sense. This makes sense. Yeah, this makes sense. Yeah, I figured like using the force on a current carrying wire, because the force has to be so high to counteract gravity. I don't think you're gonna get very far with that, right? Like it becomes not feasible very quickly. But yeah, maglev trains where you have two repelling. You have a south pole and a north pole against each other, or sorry, a north pole and a north pole against each other. They're going to repel, right? Yeah. Okay. 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 So let's quickly calculate this gravitational force here. Okay. So on the segment of wire, we know what the 4.3164. Okay. So Fg equals mg. The mass is 0.44 kilograms. The gravitational field strength is 9.81 meters per second. So let's calculate this. Yep, 4.3164, good. 4.32 newtons, approximately. Okay. Okay, and so we can immediately notice the gravitational force that's exerted on the wire is way larger than the magnetic force that's keeping it up, right? So we have a magnetic force holding the wire in the air, but we also have a gravitational force pulling it down. The thing is, the gravitational force is much, much larger than the magnetic force. So this wire is not going to magically levitate just due to Earth's magnetic field, right? Again, we would have to have a pretty significant current. Let's see what current we would have to have. So if we wanted instead the force exerted on the wire to be equal to 4.32, and we left the current blank, so we actually wanted to calculate what the current is on the same length of wire, so the same 2.5 meter length of wire, in the same magnetic field of the Earth, so 57 microtesla. Let's figure out what the current would have to be in order to accomplish this, right? So if we flip this around, that's pretty extreme. Yeah, that's pretty significant. So extremely large. Well, so with current, right, we have to consider Ohm's law, right? And so in order to have a current that high, you would have to have a a very, let me make sure I get this right, Ohm's law. Exactly, yeah, because, yeah, in order to have very high current like that, you have to have a very high potential difference and a very low resistance, right? And so if you have a really low resistance wire, it's almost like a short circuit in a way, right? Like a short circuit, if you run something through zero resistance, you get like a high potential through something with zero resistance, you get like infinite current, right? But I don't think we can have a wire support that much current. I don't know. I'm not positive about that. Like I don't know what the a really big wire, like a right. I guess the issue with that would be the mass would then be even higher than it currently is, right? So the gravitational force is then high. You know, like I don't think it's actually feasible to balance these two things out like this. Yeah. Yeah. So, any questions about that example, or any questions from any of the examples, or yeah, what are we thinking? How was that first class? What do we think? I'm actually going to pop into the